Good morning, friends. This is Professor Chaubey. Professor Chaubey's physics class under the heading Physics Made Simplest. Today I am going to talk about RLC resonance circuits, that using resistance, inductance and capacitance we can make some circuits which are called resonance circuits. There are two types of resonance circuits. One is called series resonance, that is in which R, L and C all are connected in series to a voltage source. So what will be application and use of such circuit? What the meaning of resonance circuit means? Resonance means either at resonance current is maximum or minimum. So let us see the conditions. So we will see what the conditions to achieve, to get resonances. Also see, resonance means, as I told you that there are two types of resonances. One is series. So series resonance means when the power factor of the circuit is unit, means 1. That is, power factor cos phi. Cos phi is equal to R over Z. Z is the impedance of the circuit. So cos phi is equal to 1. Means, or R is equal to Z. And Z is R square plus XL minus XC square. So R is equal to Z, and Z is this. So when this will be possible, R equal to Z means this XL, so therefore XL, so XL must be equal to XC, so that R is equal to Z, that is equal to R, that R here, XL equal to XC. So XL equal to XC means XL is twice pi. I call this frequency, the frequency at which R is equal to Z is FR. That is called resonance frequency. So resonance frequency. So that R equal to Z means XL is equal to XC. XL is equal to 2 pi omega, or you can say 2 pi, that is omega L, so 2 pi F R L. FR is the resonance frequency. And XC is 1 over 2 pi F R into C. So these two must be equal, means 2 pi F R L is equal to 1 over 2 pi FR and C. So 2 pi here, FR here, FR square. FR square is equal to FR square equal to 1 over 4 pi square LC. L and C. This means that FR is equal to under root of this, so 1 over 2 pi under root L and C. So this is the frequency called resonance frequency. At this frequency, what we get, XL is equal to XC, means there is inductive reactance and capacitive reaction both are equal. Impedance is minimum that is Z is equal to R. So the frequency at which impedance is minimum, and at this frequency, at this condition, resonance frequency FR is equal to 1 over 2 pi under root LC. This is the resonance frequency at which Z is equal to R and power factor is 1. So impedance is minimum and hence current is maximum. This means current in the circuit that is zero of current if RMS value IB is equal to EB over Z, that is EB over R, because Z is minimum, XL is equal to XC, so IB is maximum, EB over R. So this is called a circuit at, because we are talking about the alternating current, so frequency involved. So the frequency at which the current becomes maximum, that is the resonance frequency, this frequency, 1 over 2 pi under root LC. At this frequency the current is maximum. So this is a series. Series resonance circuit when current is minimum. Current in the circuit means it is maximum, because that is current is maximum. Also known as acceptor circuit. The circuit which accepts one frequency for which current is maximum, other frequencies currents are less. So we can select that frequency for which current is maximum. It means it accepts that frequency, it gives current maximum. So such circuits are known as acceptor circuit, means they accept the frequency and give current maximum. So FR, L and C, F is 1 over 2 pi over LC, and the units, of course, C, when C is farad, L is Henry, the frequency is Hertz. L in Henry, C in farad, then F is in Hertz. This is the unit. So this is a circuit which is acceptor. The impedance of the circuit. So what we conclude from this circuit? What are the main conclusions from this? A circuit RLC for which power factor is 1. What we conclude? We conclude that the impedance of the circuit is minimum. The impedance of the circuit is minimum. Okay? What else we write? And equal to R, as XL is equal to XC. The current in the circuit is maximum. These are the conclusions. The current in the circuit maximum. That is IV is equal to EV over Z, and this is simply R. So current is maximum, and it is called series resonance. A circuit, we use components such that XL and XC are opposite. One is positive, other is negative. Means one decreases current, other increases current. So another conclusion we have our third conclusion is that since in series resonance current is maximum, since the circuit is very large, and that is very large, or current is very large, I is large, so voltage drop, therefore voltage drops across circuit components is also large. What does it mean? Voltage, because current is maximum, so Ri drop, Xi, that is XL into I, Xc into I, or R into I, these voltages are large. Sometimes, because current is very large, even the voltage drops across XL and Xc are sometimes larger than the voltage applied. But since they are opposite, so total voltage remains the applied voltage, where is the voltage across resistance, capacitance, and inductors. But we know the voltage drop that is across XL and Xc will be zero total. Because both are of opposite sign. So, and they have opposite phases. $180 difference. Just one is vertical up, other is vertical down. Means one may be up, other may be down. Then may be say I XL, this is say I XC. Down, up and down. So both cancels each other. So remember that if you want to draw, if you have the input voltage of different frequencies, you apply, connect the voltage sources of different frequencies, F, vary F. Accordingly current will vary, and at certain current, at a certain frequency, the current will be maximum, and that is called the resonance frequency. So you can see the variation of you can plot a resonance curve. Resonance curve means a curve which shows the behavior of current with frequency. How the current is varying with frequency. So that is, you see, you have current current we take on this side and frequency on this side. So this, you can see that from certain point like this. For another component, so this is the FR. F is equal to FR. That is the resonance frequency. At resonance frequency, the current is maximum. Frequency changing, current increasing. At certain frequency, when XL and XC both become equal and opposite voltage, so current becomes maximum, increases. So this gives the behavior of current, frequency current curve, and this is known as the resonance curve. Behavior of current with frequency. So this is the resonance curve. How the current is varying with frequency in series. So I think this is important thing, that there is a resonance frequency for which current becomes a maximum, and also there is one important factor of the circuit, that is known as the Q factor. Quality factor, what Q factor? Voltage across L or C. This is the voltage across L or C, that is because both are equal. So what the voltage across, and the voltage across the capacity or inductance, because they are both equal and opposite. So, and then applied voltage. So this factor is known as the quality factor. So we have, say, current IR. At resonance frequency, I write current as, say, IR. And then XL divided by IR into R. R I drop. So this is simply XL over R. The quality factor, Q factor, is XL over R. That is Q is equal to XL over R. And we know that we can write, say, what the omega. Omega is equal to 2 pi FR is the angular frequency, and that we know omega is 2 pi FR. FR is 2 pi, FR is 1 over 2 pi under root LC. So 2 pi cancels, so omega is this 2 pi 1 over under root LC. So this is omega. And the Q factor is equal to XL over R. And XL over XL means omega L. So omega L, XL is omega L over R. And omega is 1 over under root LC. So 1 over under root L and C, that omega, and into L and then R. So under root L over C, we have 1 over R under root L over C. This is the quality factor of the circuit, is known as 1 over R under root L over C. This is the, well, what is the physical meaning of quality factor? That is 1 over R under root L C. So what is the physical significance? What is the physical? What is the physical meaning of Q? Physical meaning of Q is the Q factor of series circuit. The Q factor of a series RLC circuit . indicates that how many Q is 1 over R, 1 over under LC, that how many times the PD potential difference across L or C is greater, across L or C is greater than the applied voltage at resonance. One over under root LC. Q is frequency, omega into L over R. For example, consider R L C series circuit connected to 240 volt AC source. The Q factor of the coil is 20. Then voltage across L or C will be the voltage across L or C (20 into 240). That is 4,800 volt. At resonance. Vc is equal to Vl is equal to Q Vr is equal to 4,800. So Q into Vr. Now this is the series resonance circuit. Friends, I take a small break of 5 minutes or 10 minutes, then I again come to you and I will explain resonance, that is the parallel resonance circuit. This was series resonance. I will talk about the We now talk about parallel resonance circuit. As I have written, parallel resonance circuit means we have a circuit involving inductance. You know, inductance is never pure, it has got some resistance. So R is inbuilt in that. But it is the inductance and it is the capacitance. So basically they are reactance, capacitive reactance and inductive reactance. voltage source is E is equal to E naught sin omega t, or having EB as the RMS value of the voltage. IB is the current flowing in the circuit, IC through the capacitor, IL through the inductors, the circuit. Well, what the meaning of a resonance circuit? Well, resonance circuit, when this is parallel, in this parallel resonance circuit we mean the circuit where current is minimum, means these are opposing, means the inductive and capacitive currents are both opposite, so they make equal, and the total current is, say, including R here also, but total current is now such that if both are opposite, because both are opposite, I have shown like this, but value equal, then the current becomes minimum because both these are equal, so this is 0, and only resistance of this gives some resistance. So this circuit is known as the resistive circuit because it is giving current minimum. This circuit is known as resistive circuit, where current is minimum. Remember, in the series resonance circuit we got current maximum. Current was maximum. That was the acceptor circuit, means it accepts those frequencies which are giving maximum current, large current, and we will not allow the currents frequency which is giving low current. So only those frequencies are accepted which gives a current above certain limit, large current. Here the current IL equal to IC, both are opposing. So current is minimum, almost nearly 0. So then you can see EB over XL, IL equal to IC. So EB over XL and EB over XC equal. This gives XL is equal to XC. That is, the capacitive reactance and inductive reactance are equal, but effect of both are opposite. So XL is 2 pi FL and XC is 1 over 2 pi F. This frequency I am writing R, FR, that is the resonance frequency. So FR is equal to, from this, 1 over 2 pi and root LC. So this the frequency is same as the acceptor circuit. This is the rejector circuit. This circuit will not allow the frequencies to enter in this, because some frequency will give very small current below certain limit, and those frequencies will be rejected, will not be allowed. So such circuits are used in the radio transistor circuits, where we want to reject some frequency and we want to accept only one frequency for which the current is maximum. Other reject, all frequency rejected. So we reject the circuits. So those frequencies which are giving a small current, they will not be allowed, because current is very small. So such circuits are, this is parallel resonance circuit, means it will give a minimum current at certain frequency FR. And the Q factor of this circuit as defined is, XL over R, means voltage across the inductance or divided by the total voltage applied. So that gives you Q factor omega L over R, and omega L we can put here. So same as in the series resonance circuit, 1 over R and root L over C. This circuit is known as the resistive circuit, where current is minimum. Resistive means it is resisting the current, means the current in the circuit is minimum. It is rejecting the all frequencies because they give small current. So if you want to reject certain frequency, don't want to allow that frequency to give the current to the circuit, use the parallel resonance circuit. And we can see that Just like you can plot a resonance curve also. That is the frequency, and yeah, of course current is positive, so this current, so this FR, where current IV is nearly zero, very small. This also we can have current approaching nearly very small. So such circuits are known as the current is nearly zero. The frequency, resonance frequency, FR frequency, where IV is nearly zero. So this is the rejector circuit. Remember that effect of the parallel resonance circuit. What is the effect of parallel resonance circuit? The circuit power factor becomes unity. This implies that the circuit, this implies that this is resistive. This is resistor circuit. This is a resistor circuit, means opposing. Current becomes nearly zero. The impedance of the circuit becomes maximum. The impedance of the circuit becomes maximum. So that IV is nearly zero. The circuit current is minimum, that means that is the IV is minimum. The small current IV flowing in the circuit. So this is rejector circuit. A coil of resistance 100 ohm. Now I have a question. Say a coil of resistance 100 ohm and inductance 100 microcurie. microhenry is connected in series with 100 pf capacitor, picofarad, 100 pf capacitor. PF means picofarad. The circuit is connected to a 10 volt frequency to a 10 volt variable frequency source. Calculate resonance frequency. Calculate resonance frequency. Number 1. Number 2, current at resonance. Number 3, voltage across L and C at resonance. So this is the problem. Well, you can do resonance frequency. This pen was not working. Well, resonance frequency FR 1 over 2 pi under root LC. So find out 1 over 2 pi and under root 10 to the power minus 4. It is 100 pf. So 100 into 10 to the power minus picofarad, so 12. So 10 to the power minus 10 and 100 ohm. So coil resistor 100 ohm R. So that is 2 pi L and C. 10 to the power minus 4, 100 micro, so 10 to the power minus 6, 10 to the power minus 4 Henry, and into 100 pf. So 100 into 10 to the power minus 12, so 10 to the power minus 10. Well, this you can calculate 1.59 10 to the power 6. This is the frequency, and IR current at resonance is EV over R is equal to 10 over 100. Resistance 100 ohm. So this is 0.1 ampere current. VL is equal to IR into XL. So that is IR 2 pi FR into L. So that we can calculate. IR 0.1 into 3.14 into 2 pi into FR into L. So FR is 1.59 10 power 6 into L. L is 10 to the power minus 4. So that we can see 100 volt on this. You can multiply. So VL and VC is of course IR into XC. That is IR 1 over 2 pi FR into C. So this is 0.1 IR 1 over 2 into 3.14 2 pi FR 1.59 10 to the power 6 and C is 10 to the power minus 10. So that you can multiply and you will see that this value is also 100 volt. Because voltage across C and voltage across L are equal. That is the resonance, series resonance. So this gives you the solution of the problem. Friends, you do some more problems like this. We stop today here. And maybe now when we meet next time, I will start some other topic, some new topic. So thank you very much for listening to me.